Hello everyone, in this video, I will introduce our group work LinearSankoff briefly. Before we talk about the algorithm, I would like to introduce some background knowledge, homologs folding, comparative sequence analysis. For this topic, the input are several unaligned sequences that are homolog sequences. And we want to do the folding and alignment. We want to get the conserved structure. How to get it? We want to align the structures so we get common structure. There are several ways to do that. One is fold and align. We fold each sequence separately. We got a structure for each sequences. We then align the structures. Then, or we can do the alignment fold. We align these sequences as a multiple sequence alignment, and then fold the whole alignment as a one sequences. Then we got a line structure. These two algorithms or ideas proposed in order to save some time and memory, but it's not so accurate. The traditional way to do it, or more accurate to do that, is a joint fold and align. The classical algorithm proposed by Sankoff, and it's just like folding or parse two sequences together, but it's too slow. It's taken n to the power of 6 only for two sequences. So we propose the LinearSankoff make the algorithm more accurate and more efficient. There's more limitation for this Sankoff algorithm. One is too slow. Another is only focused on secondary structure. It's with a very simple alignment model, just add distance. So we propose the LinearSankoff. We incorporate a more complicated alignment model, hidden Markov model. So LinearSankoff is an intersection of CKY and hidden Markov model. So for folding, it's just a free energy change. For alignment, the score is the probability of alignment of two sequences, not just the added distance. That's one advantage. Another is we make the algorithm scale linearly with sequence lines. This idea is inspired by LinearSankoff, dynamic programming along the diagonal line, not the bottom. For example, this is the bottom-up way to do the parsing, but we make the direction, we make it another direction. We like the algorithm along the diagonal line and make it the beam search algorithm possible. So we only keep top B state based on each state scores. That means we can incredibly reduce the searching space and make the algorithm more efficient. Another thing is that we apply the A-star-like algorithm to accelerate searching. The rectangular space is what we have touched. The blue region is we haven't searched. We have a pre-processing, and we will let the stage know how far you are from the destination, but this is just the estimated score. So we will combine the inside score and estimated outside score together. We get estimated total score from the source to destination. And we will re-rank by this estimated total score and only keep the top 10. By adding this estimated outscore, we will accelerate the searching. So for example, this is searching quality against the beam size. The blue one is without A-star algorithm. The orange one is with the A-star algorithm. We can see with the limited beam size, which means with a pretty limited searching space, we can reach to a pretty high searching quality. The beam size is correlated with the runtime. If we reduce the beam size, we can also reduce the runtime. That means we can lead to a good performance with a really limited runtime. For the efficiency and the scalability, we compare with a traditional Sankoff algorithm called DiaLine. We only allow the algorithm to search in this gray area, the diagonal line region, to make sure that the comparables is fired. And after that, the DiaLine, the time complexity is n-cubic. For linear Sankoff, is scaled linearly with 6 lines, makes it easily scaled to 30,000. That's in SARS-CoV-2 lines. It's pretty long. Although there is a trade-off between folding and alignment, and there is a sweet spot between folding accuracy and alignment accuracy. With this sweet spot, we can get the highest fold structure accuracy as well as the alignment accuracy. We did the research and to find the sweet spot, it's lambda 0.3. This is the final folding accuracy and alignment accuracy. In short, that's structure prediction, linear Sankoff significantly better than previous method. For the pairwise alignment, linear Sankoff is comparable to previous algorithm. And another thing is that linear Sankoff can also do the domain insertion. What is domain insertion? There are 2 TRN structures, and this one has an inverted branch. Linear Sankoff can handle this kind of domain insertion, and due to the complicated alignment algorithm, it performs better than previous talk. There also can check our poster or code online.